All right, let's talk about the secret language of electronics. Today, we're going to pull back the curtain on the one fundamental rule of physics that makes, well, everything digital actually work. It's called band theory, and trust me, it's what makes your phone, your computer, all of it tick. So let's dive in.
I mean, just look at the device you're watching this on right now. It all boils down to a really simple principle: letting electricity flow or stopping it. It's an on-off switch, right? But the real magic, the real genius, is in the stuff that can do both. The materials that can be a conductor one moment and an insulator the next. So how on earth do they do that?
Okay, so to even begin to answer that, we've got to get organized. We need a way to sort all the materials out there. You can almost think of it like a simple sorting hat for the physical world. And it groups everything based on just one thing: how well it plays with electricity.
And the one metric that matters for this sorting is called electrical resistivity. It's just a fundamental property of a material, like its color or how heavy it is. And all it does is tell us exactly how much that material pushes back, how much it resists an electric current trying to flow through it. Super high resistivity, bad conductor. Super low resistivity, you've got a great one.
And when you actually look at the numbers, the differences are, well, they're insane. It's not like a little difference, it's a huge difference. On one end of the spectrum, you've got conductors, right? Things like copper, with basically no resistance at all. Then way over on the other end, you have insulators like glass. We're talking a resistivity that is literally over a billion times higher. And squeezed right in the middle of that enormous gap, that's where we find the really interesting stuff: semiconductors, like silicon.
Okay, so this is useful, right? It tells us what things do. We know copper is great for wires and glass is great for, well, not being a wire. But it doesn't tell us why. Why is the difference so mind-bogglingly huge? What is actually going on down at the atomic level that makes them behave so differently?
For a long time, that why was one of the biggest puzzles in physics. Seriously, scientists came up with all sorts of theories to try and crack the code. They started with the classical physics everyone knew and loved, but pretty quickly they realized, nope, the answer had to be somewhere in the weird world of quantum mechanics.
So, you had these early models, like the classical free electron theory. It got some things right, it could explain Ohm's law, which was great, but it had no idea why metal conducts and glass doesn't. Just couldn't do it. Then came the quantum free electron theory. This was a step up. It brought in some really important quantum rules, like the Pauli exclusion principle. But it still couldn't explain the big picture. It couldn't tell us why we have these three distinct groups: conductors, insulators, and semiconductors. The core mystery was still unsolved.
And then, the breakthrough. It finally happened. A physicist named Felix Bloch had this brilliant insight. He realized everyone was making the same mistake. They were looking at electrons as these lonely individual particles. He said, no, that's not it. The secret is in how they act together, as a crowd, all packed into the neat repeating structure of a crystal. And just like that, band theory was born.
Okay, so here's the basic idea. Imagine a single, lonely atom. Its electrons have these very specific, neat little energy levels, like rungs on a ladder. Now bring another atom close. Suddenly, their electrons start to interact, and to keep the quantum rules happy, those single energy levels have to split into two. Now, imagine not two atoms, but trillions and trillions of them, all packed together in a solid. Every single one of those levels splits into trillions of new levels, all crammed so incredibly close together that they just blur. They merge into these continuous energy bands.
So within this new picture, you've got three main characters you need to know. First, there's the valence band. That's the highest band that's usually full of electrons. Think of it as the home level. Then, above that, there's the conduction band. This one is usually empty, and it's like the freeway for electrons. If an electron wants to move and create a current, it has to get up into this band. And the space between them? Now that is the most important part of this whole story. It's called the forbidden energy gap, or just the band gap.
And really, that's it. It's all about the gap. The size of that band gap isn't just some minor detail. It is the one thing that perfectly, beautifully explains why a conductor, an insulator, and a semiconductor are what they are.
Let's take a conductor, like copper. What does its band structure look like? Well, the valence band and the conduction band actually overlap. There's no gap at all. They're basically touching. This means electrons can just slide right over into the conduction band with almost zero effort. It's a wide-open superhighway for electrons. And that is why metals are such amazing conductors.
Okay, now let's look at the opposite extreme, an insulator.
In this case, the band gap is massive. It's like a Grand Canyon between the valence and conduction bands. For an electron to make that jump, well, it would need a huge amount of energy, far more than it's ever going to get under normal conditions. So the electrons are just stuck. They're trapped in the valence band. And that means no current can flow. Period.
And this is where the magic happens. The semiconductor. It's the Goldilocks material. It has a band gap, yes, but it's not too big and it's not too small. It's just right. It's like a small stepping stone instead of a giant canyon. So, if it's super cold, it acts like an insulator. No electrons can make the jump. But if you give it just a little bit of energy, say from some heat or a bit of light, a few electrons get just enough of a kick to hop across the gap and into the conduction band. And bam, you've got a current. This ability to be switched on and off, that is the entire foundation of every piece of modern electronics.
So you see, figuring out this whole band gap thing wasn't just for a bunch of physicists to pat themselves on the back. No way. This was the key. This unlocked our ability to engineer materials, to actually control things at the quantum level. And that led directly to, well, everything we use today. But wait, there's more. The rabbit hole goes a little deeper, because it turns out that not all band gaps are created equal. The way the bands are aligned, their exact shape and position relative to each other, has massive implications for what a material can do. And this gives us two main flavors, direct and indirect band gaps.
Here's the difference, and it's super important. In a direct band gap material, like gallium arsenide, when an excited electron falls back down from the conduction band, it can do so in one clean step. And when it does that, it releases its extra energy as a photon, a particle of light. This is why these materials are amazing for things like LEDs and lasers. But in an indirect band gap material, like our good friend silicon, the electron can't just drop straight down. It has to take a detour. And in the process, it releases its energy as a phonon. And a phonon is just a bit of vibration, basically heat. So silicon is terrible at making light, but it's absolutely perfect for making transistors and solar cells.
And really, that is the core idea I want you to walk away with. It's not just that these band gaps exist. The truly revolutionary part is that we figured out how to engineer them. We can pick materials with just the right kind of gap for the job. We can add impurities, a process called doping, to tweak it. We can build entire devices that are designed to exploit these weird quantum properties. And that ability, is the absolute bedrock of all modern electronics.
So think about it. We started with a pretty simple question. Why is copper wire different from a glass window? And the answer, band theory, completely unlocked a revolution. It gave us the transistor. It gave us the microchip. It gave us the entire digital world we live in. So it really makes you wonder, right? As we keep discovering and even creating brand new materials with even more wild and exotic band structures, what's the next thing we're going to build?